study the algebraic properties of Steinberg modules, and they'll get sort of increasingly exotic, and eventually the word doidal will appear. But today we're just going to think of them as rings. So we're going to think about the multiplication map between Steinberg modules. And in order to think about it properly, I'm going to argue we need to view it this category of representations of groupoids. So sort of a goal is to get comfortable doing algebra in representations of groupoids. And a second goal is to basically think of the, well, answer like Dick Haynes' question, like, what about congruent subgroups? So I want to think about, generalizations of the Church-Farr-Putnam conjecture, and more important than thinking about generalizations, I want to rephrase things in terms of, I guess, like I'm a homological stability person, so I view everything as stability, and I want to sort of sell a representation stability, homological stability perspective on Steinberg modules. Okay, and today R will be a PID. You can probably get away with a Dedekind domain everywhere if you're less lazy. F will be the field of fractions. K will be the name for my coefficient ring. We're going to need like a name for a fourth ring later. I'm running out of letters. Okay. I'm going to go with lambda unless someone can think of a more convenient name for it. Okay. Yeah, so we're going to review, the first third of Jenny's talk quickly.
Is K a field?
No.
No.
Okay. Well, I mean, K. Sometimes K will be Q. Sometimes K will be Z. Yeah. So the Tietz building, so if V is a free R module, T of V is the realization of the poset proper cell, non-zero summands of V, ordered by inclusion. Am I supposed to be tall? What is that? The usual? Is this the usual? Do people write on the higher one or the lower one?
The higher one.
Higher one. Okay. Yeah, ordered by inclusion, and so elementary proposition is that the Tietz building. I should say T N R is my notation for T of Rn. This is isomorphic to, so if you have a PID, the Tietz building for the PID is isomorphic to the Tietz building of the field of fractions. So if you have W contained in R to the n, you can send it to W tensor F. And if you have U contained in F to the n, you can send it to U intersect R to the n. Okay. And the Solomon-Tietz theorem says that also this simplicial complex is n minus 2 dimensional. The theorem says it's n minus 3 connected, so in particular it's homotopy equivalent to a wedge of n minus 2 spheres. And we define the Steinberg module to be the only interesting reduced homology group of this space. So V rank n, Steinberg V, is defined to be the reduced n minus second homology of the T spelling. Jenny, I'm also struggling with the n's versus b's. It's hard. Yeah. And then we have natural. There's a nice description of these spheres, or a nice description of generators of this group. So for B, a basis, there's a apartment, or A of beta. This is the whole subcomplex. Basis. So, V, whole subcomplex of the Tietz building of spans of proper non-empty subsets of the basis. And it's important to draw this picture of a triangle every time you give a talk on Steinberg modules. So if you have a basis B1, B2, B3, here, better than the conference we organized where this was drawn like about 8 times.
We haven't gotten to the end of the week here yet.
Yeah. I might not draw it again. I'm not. So, in general, these complexes are isomorphic to, you take a n minus 1 simplex minus its top cell and barycentrically subdivide it. So in particular, these are homeomorphic to n minus 2 spheres, those spheres, and we let class beta, this is the image of the fundamental class of this sphere in the topology group. How'd you deal with like the chalk getting wet?
Oh, I did a bad job.
Use different chalk.
Sorry.
You different chalk. Okay. Yeah. And to make sense of this, instead of the basis being a set, maybe it should be a ordered set. Because we need to know what, do you go around this way or the other way? Okay. And as Jenny mentioned, these apartments are generators. So theorem Ash-Rudolph says that if R is Euclidean, Steinberg V is generated by by these apartment classes. Okay, so with the setup, we can define
By integral.
Yeah, it's
the set of basis.
Is V here in our module?
Yeah, that's how I.
So three
He
bases.
only takes it in our module.
Yes.
Okay.
It stands for module.
Okay. Okay. So.
So sorry, generated as a GLV module. What's the?
I mean, so if you want to take one apartment, it'll generate the whole thing as a GLV module. If you take all the apartments, it'll generate it as an abelian group. So however you want to. Since this is ambiguous, but you can parse it either way. Okay. So now we can define multiplication for Steinberg. Yeah. So there's a definition. So for our Euclidean, let mu goes from Steinberg n r tensor to Steinberg m r to Steinberg n plus mr be, well, if you have a basis v1 through vn, giving you an apartment class in Steinberg nr, and you have another basis w1 through wm in Steinberg n plus mr. You map it to that. Now, you could have some objections, like why is this well defined? And for the integers, Jenny told us what the relations are, and you can just check that those are valid relations. That's one approach. There's sort of maybe a more elegant approach due to Sander, Oscar, and Soren Glacius, where they describe this at the space level and the level of the double suspension of the Tietz building, and then this is just induced by direct sum, and you don't need to say the ring is Euclidean, and it's sort of manifestly well defined, and then you can check, or you meaning, or one can, and in particular they did check that this agreed with this formula, which I guess,
Yeah.
and
Jeremy?
yeah.
Am I supposed to interpret V as V, comma 0 in the decomposition of R n plus m into Rn plus Rm?
Yeah, I'm about to criticize this definition for like those types of reasons. Yeah. Oh yeah. So this, this uses, your favorite, and the problem is maybe different people would have different favorites. There are at least two different good choices. Yeah. Okay. So I was going to present whatever your guys' description, but every talk has been running over, so I'm going to skip that. Yeah, but this is well defined, and okay.
Sorry, Jeremy. So to check that it's well defined, you need the Bajkowski presentation for any Euclidean ring. Is that correct?
Yes, which we have for every field, and Steinberg R is the same thing as Steinberg F. So
Okay.
you can Bajkowski doesn't give a presentation for Steinberg modules for lots of Euclidean rings, and I mean lots of PIDs are not generated by apartments. Nevertheless, this product. Yeah. So one way of defining it for all PIDs would just be define it for fields and then use the Steinberg of a ring Steinberg of the field of fractions, and then check that, using Boykovsky, you could check it's well-defined. Or you can, write it down on the space level, and then it doesn't use, then it just, tells you, you send submodule and another submodule to their direct sum, and then that's clearly well-defined. Okay, so the proposition, you just take the direct sum, Steinberg modules. This is associative ring. The problem is that it's not commutative, even in a graded sense. And that's why we're going to have to leave sort of usual algebra land and go to representations of a groupoid. Okay, so it's not commutative. So, for example, E1, tensor E1, E2. So this is in Steinberg 1. This is in Steinberg 2. I don't know. This goes to E1, E2, E2 plus E3. On the other hand, tensor E1. This goes to E1, E1 plus E2, E3. Using, n being the first n coordinates. If you change conventions in the middle, you could get them to be the same. That's what we're going to do. So I'm going to use a different name for the groupoid that Oscar talked about because it may be more politically aligned with the American representation stability community. But otherwise, it's the same.
Yeah, sorry, this is maybe a minor point, but I'm not sure. From my talk, maybe Steinberg 1 doesn't make sense, or what?
Steinberg 1 is Z.
Great, okay.
It's H minus, it's reduced H minus one of the empty set, which is Z.
Sorry, yeah. More controversial, Steinberg 0 is also Z. Which, yeah.
Steinberg 0 is generated by the empty apartment. Steinberg 1 is generated by the single line apartment.
Yeah.
That's by definition, maybe, if you want to.
Yeah, like the.
That's not a proper subspace of one-dimensional.
No, but if you take the boundary of this zero-dimensional simplex, it's the empty set, and that's exactly what T1 is, the empty set.
We'll go with
-1 homology.
We'll go with like the Oscar's twofold suspension, and then it's the zeroth homology of a space that's contractible. So then we're good. But yeah, I haven't used Steinberg 0 is Z, even though the definition I gave would give something else. Okay. Okay, so VB modules. Okay. So VB is a category. The objects of VB are, I'll usually suppress R. These are free, finitely generated R modules. Between two of them is a set of isomorphisms. Mod VB is the set of functors from VB, I don't know, to, let's say, abelian groups. Maybe it'll be chain complexes, maybe it'll be spaces. Okay. So, the skeleton of VB is just the general linear groups. So a VB module is just the data of a collection of abelian groups Mn, and where Mn is a GLM representation.
It might be worth saying that the ends start at 0. Yeah. On the right hand side too. Or whatever.
Oh, yeah. N equals 0.
Yeah.
Infinity.
You want K modules instead of abelian groups?
Maybe.
Yes.
Yeah.
Yes.
I mean, K modules are abelian groups.
You said K.
I said my coefficient ring. But I mean, maybe that just means I'm taking homology with coefficients in K, which gives you an abelian. We'll go K module. Eventually I'll write tensor product and probably. Okay. Yeah, so the two most important examples in this talk are going to be this K underline from Oscar's talk. So this is just the sequence. It's K in every degree. The other example of a VB module will be Steinberg. So this sends V to Steinberg of V. This sends V to K. Decategorified, this is just the sequence of Steinberg modules. Steinberg N. And so we want to do, what problem are we trying to solve? We're trying to solve the problem that this ring is not commutative. And so what we want to do is we want to say this thing is a ring and is commutative in a graded sense. So we need a monoidal structure on VB modules, which is it's going to be day convolution. Oscar already mentioned this. And yeah, so for M and N, VB modules, meaning you plug in an R module into M, you plug in and it gives you something, you plug in an R module into N, it gives you something. I want to tell you what their deconvolution tensor product is. So to tell you what it is, I need to tell you what it outputs on some R module V. And so this is going to be the direct sum over ways of writing V as an internal direct sum of A plus B of MA tensor NB.
That tensor is K.
Yeah, that tensor is K. That's when I decided to agree with Peter, when I realized things. Yeah, so you want to think of this maybe more concretely. This corresponds, this value on Rn is ind GLN, direct sum A plus B is N, GLA, GLB, GLN of M evaluated on RA, tensor M evaluated an RB. Yeah, so now, if you have a monoidal structure, you could talk about monoid objects, which we're going to think of as rings. So a VB ring, it goes right at the VB ring. It's just a monoid object. Mod VB with a convolution. I guess Day is someone's name, but I'm not capitalizing it. Yeah, and our main examples of VB rings are these two things. Here we just use the map K tensor over K with K goes to K. Standard isomorphism. And here on Steinberg modules, we use this apartment concatenation map. I don't know, maybe I erased it. No, yeah, that thing over there. And now, so, you know, with this perspective, Steinberg is commutative in the graded sense. So if you want to say it's skew commutative, or if you want to add an extra homological grading, this K underline is also commutative. So, you know, so if you try to run this example, you wouldn't have this awkward thing of you know, turning this E1 into an E3. This E1 would be a basis of R1. This is a basis of R2. And, all right, maybe I'll say, so if, example, let's say, you know, W has basis W1 and V has basis V1, V2, then this goes to W1, V1, V2, and this goes to and then these two are equal. In general, they're only equal up to sign, but I think it's an even permutation here. Okay.
No, it's
Okay. And I.
Sorry.
Yeah.
That's right.
Oh.
You haven't really pointed out the crucial fact that the Day convolution is symmetric monoidal.
Oh,
So
yeah.
it's meaningful to say something's commutative.
Yes.
And somehow the point is that the symmetry is interesting.
Yeah. Oh.
Are you going to explain that?
No, but I think I'm also going to run out of time and not say what I planned on saying in other ways as well. So the Church-Farr-Putman conjectures say that HI of S, L, and Z with coefficients in Steinberg. Here, take K to be Q, is 0 for n greater than or equal to plus 2. And yeah, so this is interesting because as Jenny talked about, this is isomorphic to H n minus 2 choose I of SL and Z. So it's a conjecture saying that codimension I cohomology is eventually 0, n large. So yeah, so the first goal is to rephrase this as a stability conjecture. So here's a remark. If lambda is a VB ring, then the covariance, the SL covariance, so this is just my notation for the direct sum over all n of H0 SLN, with coefficients in lambda n, then this is an n-graded ring. And HI SL, coefficients in lambda, this is just a direct sum. SLN with coefficients in lambda n. This is a H0 SL module. And maybe it's more natural to be doing GLN here, but simplify the story. I'll just say SL. Okay, so maybe let's see what are these rings? H0, SLZ with coefficients in Steinberg. Yeah, well, Jenny mentioned that well, let's just say what this is. So Jenny mentioned that Lee Sharba proved that this is 0 if n is greater than or equal to 2. And then it's not that hard to check that this is, let's say, K is still Q. Q, if n is 0 or 1. And if you think about it, the ring structure is exactly just the exterior algebra on one class, where this is in degree 1. So the generator, so when I is, when n is 0, you get the unit in this ring. When n is 1, that's generated by x. X squared is 0. So yeah, maybe a remark. If M is a lambda x module, with generators, in degrees or in grading less than or equal to D, then Mn is 0 for n greater than or equal to D plus 2. Because, yeah, so if this is a module and its generators as a lambda x module all live in grading or 0 through D, then every element of M is a product of those generators and elements of this ring. But this ring is 0 starting in grading 2, so everything in the module needs to be 0 starting in grading D plus 2. So we can reformulate, this is in their paper, the Church-Farr-Putnam vanishing conjecture reformulated.
Just to relieve any kind of confusion, I just want to point out that the lambda on the left-hand side is an exterior power.
Oh, good point.
The lambda on the right-hand side is the name of a VB ring called lambda. Those are two different lambdas. Just
Oh yeah.
if that is confusing to anyone.
You can change the lambda on the right to an A by adding a horizontal line.
These are all A's. Okay, great. That's the lambda. Great. Yes. Okay, so this is HI, SLZ, coefficient in Steinberg is generated. Q is generated in degrees less or equal to I as a okay, this is slightly stronger, but this version implies this version. Okay. So there's this picture that I believe Jenny drew. So this is supposed to be a picture. HI. SLN. Homology or cohomology. And we have this range where the homology is 0. And then we have, if you go parallel to the virtual cohomological dimension, this is conjecturally 0. And if you go parallel to, if you go in horizontal lines, you enter the stable range. Yeah, so now I want to make a similar statement involving homological stability in this language. And then okay, so
The x-axis is n and the y-axis is I.
and that's I. So H0 SL with coefficients in K is a polynomial ring. And what is that? Theorem. So originally due to Borel with the worst range, the range I'm going to state is due to Lee and Sun. It says HI, SL, and Z, Q coefficients, surge X, or I guess this map, is surjection for I less than or equal to n plus 1, and an ISO I less than or equal to n. And
So I have a comment on this theorem.
yeah.
So years ago, I needed corresponding result for the symplectic group.
Yeah.
And if you look in Borel's paper, he gets a stability range that's something like the rank over 4.
Yeah.
But I asked him if, you got a much better stability range, and he went away for 10 minutes and came back and wrote me a one-line letter that said yes. The answer to your question is yes. But he knew a very strong stability.
Yeah.
The stability for arithmetic groups depends on how split the torus is. And the more split the torus, the better the stability range.
Yeah, I don't know the history super well. In papers about symplectic groups, I've seen the remark that Borel knew this. I haven't seen it for SL, but it's possible that we just didn't know that Borel also knew it.
It's some computation with roots and weights that are rational over the field. So if the torus is split, all the roots are defined over, say, Q. If
Yeah.
the root's Q split, which this is.
Okay, yeah, I'm not qualified to.
Maybe it's worth pointing out that Lee and Sun also have good ranges for the symplectic group and all kinds of algebraic groups.
Yeah, so you can rephrase this as this Borel theorem as a statement that regulation that HI SLQ is generated in degrees less than or equal to I plus 1 as a H0 SL Q underline module. I guess missing an underline. And presented in degrees less than or equal to I plus 2. So the degrees of generation of this module is a module over this ring, which is just a polynomial in one variable, that controls surjectivity, and where the relations are controls injectivity. So you can take this sort of reasonable sounding theorem and turn it into a more algebraic theorem. How long do I have? I don't know when I started. What? 5?
6 more minutes.
6 more minutes. Okay.
Jeremy, just checking that I understand. So this x that you wrote, small x in k brackets x, is coincidentally the same x as over there?
They're both happen to coincidentally be generated in degree 1.
And that's the thing that was sigma in Oscar's lectures.
Yeah, yeah. This x is Oscar's sigma. Yeah. So. I'll just give like I have probably like 20 minutes worth of notes on subgroups, so I'll just give like a 4-minute version of that. Yeah, so talk about the principal congruent subgroups, gamma and L. This is going to be the kernel of, I don't know, I'll say SLN Z maps to SLN Z mod L, the kernel of the mod L reduction map. And theorem from the 70s due to Lee and Sharba. And this says that, maybe I'll do two theorems to them. So one theorem says, gamma n3 with coefficients in Steinberg. So this is the top homology of the level 3 congruent subgroup. This is Steinberg and
HN, right?
H, what did I say? H is 0 is Steinberg of F3. So in particular, this is growing. It's non-zero and growing fast. What is this? This is perfect. Z to the 3 to the and choose 2. And another theorem, so for n bigger or equal to 3, they proved H1 just with coefficients. This is for NEL, Z mod L is little SLN. Z mod L, so trace zero matrices.
True with Z coefficients.
Z coefficient? Oh, with the Z coefficient.
Z mod L.
Z mod L, yes. So, what you're supposed to notice if you, do I have my, did I erase the important? You have, for congruent subgroups, at least in these two examples, you have another kind of stability. So it doesn't stabilize as abelian groups, it's growing, but as representations. So the SLN Z mod L acts on the homology of congruent subgroups, and as representations, if you go parallel to the VCD or you go horizontally, so you fix either fixed dimension or fixed codimension, you get a uniform description in terms of representations. So in some sense, this description doesn't depend on n. This description doesn't depend on n, or at least it depends in a systematic way. And this is instances of representation stability, which can be sort of captured in this language of VB modules. But I'm out of time, so I'm not going to say that. Conjecturally in high dimensions, like proven in fixed codimension.
Questions?
Is it a conjecture that you have representation stability in high dimensions and low? I didn't get the last part.
Oh yeah, so it's a theorem that there's representation stability. What does representation stability mean? Yeah, so it's a theorem that HI gamma with coefficients in K underline is generated in finite degree as a module over H0 gamma coefficients in K underline. So this is a theorem, or like originally due to Andy Putman. So this is saying we have stability in these green arrows. If you replace K underline with Steinberg, it's a conjecture due to me, Peter, and Rohit Nagpal, it's sort of trivially, trivially true in codimension 0, and then we proved it's true for level 3 in codimension 1. It's, you know, presumably a harder conjecture than the Church-Putman vanishing conjectures. It implies it. And so the conjecture would be that H0 or HI gamma with coefficients in Steinberg, which you need to think of as a VB module, is generated in a VB sense over the VB ring gamma with coefficients in Steinberg. That's the analog for.
Maybe even more analogously, you could define a K underline for the VB, FP version, and then even H0 would be finitely generated over this K underline, similarly to how you have homological stability up there, and K underline is literally just an equivariant version of Kx. I don't know that.
I didn't understand that.
So if you didn't understand, nobody did. Never mind that.
When this homology of this arithmetic group give you some information of the modular form of the congruence groups?
I don't know any number theory, so we're incapable of using information like that. Yeah, I mean, all of our techniques are either like combinatorial topology proving simplicial complexes are highly connected, or homological algebra, you know, like exploiting highly connected simplicial complexes.
We in some sense have for n equals 2 modular curve coming in modular forms for gamma and 5 or something.
Oh yeah, someone should have said like what's special about 3, and that's a whole other talk, and you know, element, you know, if you're bored on the hike, figure out why this is, why you can't replace 3 with L when n is 2, and like it's because like modular curves have genus and things like that.